Morning, students. Am I audible? Okay. So the next topic we are going to deduce hydraulic exponent for critical depth. So you write down this. Okay. This is our next topic. We are going to derive a general equation for hydraulic exponent capital M for computation of critical depth in open sea. So first you write down this. What we are going to discuss in this topic, we are going to derive an expression or a general equation for hydraulic exponent, that is capital M, which is denoted by capital M, for computation of critical depth in open channel. Okay. So we all know condition for critical depth or condition for critical flow. I think we have already derived this expression. So you write down this expression: Q square T by GA cube is equal to 1, and put equation number 1. This equation we have already derived. Okay. Then in the next line, Q square will be there. Okay. And we will keep. So what will be here? The AQ divided by T. It's Q square by G from this equation. Okay, from equation 1, Q square by G equal to AQ divided by T. Okay. So this term we can write Q by root over G, Q by root over G whole square. Okay, we can write this, or is equal to A by Q divided by. Okay, so you can write this. So in again, if you simplify, you can write this way. Q divided by what G is equal to A to the power 7. Or you can directly write this equation is equal to A 3 by 2 divided by A to the power half. Okay. So you can write like this also. As it's divided by, so you can write A to the power minus half also. And from definition, we know if Q divided by root over G, we can say it's a section factor, which is denoted by capital Z. So in place of this, we can write capital Z. In place of Q divided by root over G, we can write capital Z, that is a section. So we can substitute here Q by root G as section factor, that is Z, and we consider this as equation number. Consider this equation as equation number 2. So that section factor can also be written in this way. That is your Z square is equal to C, that is a constant, multiplied by Y, that is your depth of flow, to the power M. I think, yeah, this derivation and what we have derived for uniform flow, that hydraulic exponent is of similar type. Okay? Or this Z square, or what you say, that section factor, can also write with this equation, where you can write that C is a constant, M is your hydraulic exponent for computation of critical flow, or you can write in open channel. Okay? H square equal to C y to the power M. For then you need to find an expression for this M. You can write this capital M. Okay? Consider this as a capital M. So you can write where C is a constant and capital M is hydraulic exponent for computational flow of computation of critical flow in open channel. Now we are taking log again. Next step is to take log. Taking logarithm in open channel in equation 3. With z square, I think now you are familiar with this logarithm. Twice log e z plus log e c plus again e to the power m. So it will be m log e y. Then we are going to differentiate with respect to y. The above equation is we are going to differentiate with respect to y. If we differentiate twice with respect to y, so dd of y log ez. If we differentiate a constant, log ECC is a constant, it is 0. If we differentiate log y, say 1 by y, then that is y. If we differentiate, because m is again is hydraulic exponent, it's a constant. We are not going to difference m. Okay? If we difference differentiate log e y, so it will be 1 by y. That is why it will be m by y. So this is 0, so we can write this directly m by twice y. From here, we can bring this 2 in the right hand side. So m by twice y. Okay, consider this as a question number 4. Good. This is our last equation, that equation number 4. Now again we take logarithm of equation number. And go back to the equation number 2. In this equation, we are going to take logarithm. Okay? So in log e z, then we have 3 by 2. Here we have 3 by 2. So it will be 3 by 2 dA by dy. Oh, sorry, it's a logarithm. So log e a minus half log e t. Because t to the power minus half is there. That is why it's negative. Taking log through equation number 1. We are going to take logarithm for equation number 2. Equation number 2, if you remember, z is equal to a to the power 3 by 2 plus, sorry, multiplied by t to the power minus half. Okay. So if you take log, then it will be log e z plus 3 by 2 is equal to 3 by 2 log e a. Then t to the power minus half, so that is why it's negative. Okay. Negative half log e t. And again, we are going to differentiating with respect to y, the above expression. And we will get again d by dy log e z is equal to 3 by 2 is a constant, log e a to be or 1 by a, and again a is not y, okay, but a is a function of y, so it will be again dA by dy, okay, minus 1 by twice t, because log e t, if you differentiate, then it will be 1 by t. Okay? But that t is not the y, but t is a function of y. So you can write dt by dt. Simple differentiation. Then after this equation, the left hand side will be same. Here it will be 3 by 2 dA by dy. Again, I think we have discussed this many times. D is equal to dA by dt for a small element. See here. So, place of dA by dy, we are going to substitute. So that is why it's 3t by twice a minus 1 by 2t dt by dy. And put equation. If you see in equation 4 and 5, our left hand side are same. Okay? For equation 4, 5, left hand side is same. Okay? Equation 4, we have e log z by dy is equal to m by twice. So we are going to substitute here by twice y is equal to 3t by twice a minus 1 by twice t dt by dt. This 2 will be cancelled out. Then you can get an expression for m. Y we are going to multiply in right hand side. If you multiply it by y, so it will be 3yt divided by a minus y by t dt by dy. This is your final expression. You can say it's the final expression of hydraulic exponent or critical flow in open. Very simple. First, you have to consider this critical flow condition that q square t by gaq is equal to 1. So then you have to bring that section factor, that is q by root over g, and you replace that q by root over g by a section factor, that is your capital Z. Then you have that equation for z square equal to c y to the power m. Then you take logarithm, then you differentiate. Then that equation number 2 also you take logarithm first and then differentiate. And then you equate both the equation and you can easily find out the expression. I don't think so. It's very simple. Okay. Only you have to take first logarithm and then you have to differentiate. Okay, done. Then we solve one numerical and then we move on to our next thing. This is the last numerical. Let the your specific analysis. We are going to complete this numerical with this class, and in the next class we are going to start our new unit. That is our unit number 4. Gradually varied flow. Okay. So you write down the question. Okay. We are going to consider only these two. Okay, rectangular channel and triangular channel. So what is given? That calculate the critical depth YC. So we need to calculate critical depth corresponding specific energy for the following different shapes of the channel. When discharge is 8.5 meter cube per second. Rectangular channel, the width of the channel is given 2.5 meter. For triangular channel, I think we all know that we don't have any width of the channel for triangular channel. Okay, so the side slope is given on vertical Z. Okay, side slope is given of the triangular channel. Okay, so first you consider, I think that the rectangular channel, this type of numericals we have already solved. Okay, so you have to find out the critical depth first, that is YC. Then you need to find out the corresponding specific energy. For rectangular channel, width of the channel is given, that is 2.5 meter, discharge is 8.5 meter. You all know for rectangular channel YC is equal to Q square divided by G. We can write here. Write here. Use this equation and find out the YC value. Q is we already know, that is discharge divided by width of the channel. The discharge is already given. Width of the channel is also given, so you can easily find out the small q value. Substitute here. G, I think you all know 9.81. Then you find out the YC value. Calculate the critical depth, okay, pi c and corresponding specific energy for the following different shapes of channel. The discharge is 8.5 meter cube per second. So you consider only rectangular and triangular channel. Okay. How much you got YC value for rectangular channel? The critical depth. YC for rectangular channel, you are going to get almost 1. Over, then you find out the specific energy that is. We all know it's 3 by 2 YC. Since we have already derived, okay? 3 by 2 YC. So specific energy for the depth YC is a relation of 3 by 2. C is equal to 3 by 2 YC. You substitute the YC value here and find out the EC for rectangular channel. So what we are going to do, we are going to end this meeting here. We end this meeting here, and then after 5 minutes, we are going to again start another meeting, okay? And we are going to discuss the next part in second meeting. Thank you, students.